One final example, not at all intimidating. Here, take a look. We're going to integrate this rational function, and we have a quadratic on top of a cubic. Not going to read that thing off. You can see it for yourself, but what I do want you to notice is that the degree of the bottom is one more than the degree of the top, which means that this is approximately in the form of a du over u, right? Because if you had an x cubed on the bottom as your u, it's cubed, then your du would be, let's say, something like a 3x squared. Now, not everything matches up, but this tells us that it is a pretty good candidate for partial fraction decomposition. So that's what we're going to try to do. But remember that the first step is to factor the denominator here. So we have had a cubic that we've had to factor before in this lesson, and it was pretty easy because everything had a factor of x in it. Not the case here. So we're going to have to rewind back to Algebra 2 and Pre-Cal and use the rational root easy for you to say, the rational root theorem, which stated that any rational zero that you have is of the form factor of the constant divided by a factor of the leading coefficient. Leading coefficient is 1, which makes this a little bit easier. So really, it's just a factor of the constant term over here. And what we have is possibly x is equal to plus or minus 1, 2, 3, 4, 6, or 12. You know, just a handful of possibilities. So who knows? Maybe you try. You remember you do this by synthetic division. Plus or minus 1, those are usually the easiest ones here. So notice we're not missing any of our terms. So we've got a 1, a negative 6, a 14, and a negative 12. Bring down the 1, multiply, add, multiply. Let's see, a negative 5 gives us a 9. It's not going to work, right? Okay, so I'm not going to finish it off. Maybe we try something like negative 1. So 1, negative 1, negative 7. Multiply 7. It's not going to work either. Okay, all right, no worries. Because you know what? I've got some more to try. Like, here, let's try number 2 here. 1, 2, negative 4, negative 8, positive 6. Uh-oh, 12. There we go. We found it. Okay, so we have successfully factored this as a linear factor and a quadratic factor. Hey, but look at this quadratic factor. So usually what happens, remember, is that you factor out a linear, then you have a quadratic left over that you want to factor, x squared minus 4x plus 6 here, and then you try to factor that, except for your factors of 6 include 1 and 6, and you get 2 and 3. There's nothing you can do with those two things in order to get a negative 4, which means that this sucker's prime. Oh man, just go ahead and erase it. This sucker's prime. You're not going to factor it. So that's kind of an issue. Hey, but whatever, we'll just go with it. So far what we've got is that we have rewritten this as the indefinite integral 2x something, 2x squared minus 6x plus 8 over x minus 2, there's the factor that we divided out, and then we have an x squared minus 4x plus 6, right, dx. All right, that's what we've got so far. Close those parentheses. And, all right, so we're going to do partial fraction decomposition, but we do have a slight issue here on this quadratic term. That's down here in the denominator, that's irreducible quadratic factor. Hey, this is getting on my nerves, so I'm going to clean this thing up right there. Boop. Okay, that's better. Now, if you watch the optional video, we know that if you have a quadratic term that you're going to do partial fraction decomposition on, it's not as straightforward as the one for the linear because it needs to be of this form. It has to be of a du over u if we're going to apply that natural log to it. So, for example, if you had, in this case, we have something like u being equal to an x squared minus 4x plus 6. You take its derivative, du is equal to a 2x minus 4, which means in general, the numerator needs to be something like this, ax plus b, right? Where we have some constant term not constant, we have some coefficient times our x and then some sort of constant term. Okay, which means I'm going to undo all of this integral here and just turn this into my partial fraction decomposition. I've got a over x minus 2 for our first factor there, and then plus, I'm going to set it up like this for our numerator. It's got to be a linear factor. Next variable in line is a bx plus c over our quadratic term, x squared minus 4x plus 6. So full disclosure, absolutely under no circumstances will something like this appear on your AP exam. So on the AP exam for partial fraction decomposition, it is specifically non-repeating linear factors. That's it. So no quadratics. So this is just extra, just because we can, because then it's also very enjoyable. Okay, so I'm going to multiply by the common denominator here, which of course is this thing, to get rid of these denominators over here, leaving me with a 2x squared minus 6x plus 8 is equal to a, and remember when I multiply by common denominator, this one will be gone, and it'll be left with the quadratic term that's over here, x squared minus 4x plus 6 plus, okay, and then when I multiply by the common denominator, this quadratic denominator will disappear, and I'm just left with the x minus 2. So bx plus c and x minus 2. Okay, so as far as this basic equation goes, we could very easily choose something like x is equal to 2, and we can get both of these to disappear in order to get the a. But the problem is choosing some value for x over here to get a to disappear so that we can get something like we can get 0 in order to get our C, but we're still left with, like, what do we choose to make the A disappear and the C disappear to get to B? Which means the better option here is a matrix and equating the coefficients. That's what we're going to do. So we're going to expand out this right side, distribute the A through. We have ax squared minus 4ax plus 6a, right? And then we'll have to FOIL this gentleman over here. When we do, we'll have a bx squared minus 2bx plus cx minus 2c. All right, and then we want to group the coefficients together. We've got a plus b x squared. Right, and then now for the x terms, there's one there, there's one there, and there's one there. We got all three of them. So put a plus sign here, negative 4a minus 2b, and then plus c. And then finally, our constant terms, we only have two of them. We have a 6a minus 2c. All right, and now we start equating our coefficients. Like, for example, a plus b should be equal to 2. So there's our first equation. A plus b is equal to 2, right? All right, and then choose a different color here. How about green? Yeah, that should work. All right, so all of this should be equal to a negative 6. So here's our next equation. Negative 4a minus 2b plus a c is equal to negative 6. And then we've got one more. How about this bluish color here? Haven't used it. That should be equal to 8. All right, so what do we got? We've got a 6a, skip a b, minus 2c is equal to 8. All right, we want to throw this in a matrix, and this matrix will look like we have a 1 for an a, we have a 1 for a b, we have nothing for our c, should be equal to a 2. We have a negative 4, negative 2, 1 for our c, and then is equal to negative 6. Last row, we have a 6 for A, nothing for our B, negative 2 for our C, and then it's equal to 8. So then we want to RREF this thing. In the calculator, which I'm about to pull up right here. Just give me a sec. Guys, come on, give me just a second. Okay. Right over. Yes. All right, this looks good. Turn this guy on. Oh yeah, it's already on. All right, so remember that this is under the matrix menu, so I'm going to go second. Matrix, I just want math. It is an alpha B. There's our REF for us. And then keyboard shortcut is alpha F3. And the size of our matrix, if you recall, was a 3x4. There are 3 rows. There were 4 columns. Hit OK on that thing. It's going to auto-populate just a whole bunch of zeros in there. Just type in the numbers that we have. And I have this memorized, guys. Don't worry about it. So it was a 1, a 1, a 0, and then a 2 for our top row. All right, let's scroll over to the second one. It was a -4, a -2, a 1, and a -6, I believe. So a 1, -6. Okay, this is riveting, right? Just watching somebody punch numbers into the calculator. All right, the last row, if I'm not mistaken, was a 6, a 0, a -2. I'm going to go with a -2, and then 8. Yep. Hit enter on this thing. Let's see what it says. And it goes, what the heck is this? All right. So this is saying that A, first position, is equal to 2, obviously. B is equal to what the heck this thing is. This is scientific notation for something that is trying to be 0, right? So you've probably seen this in your calculator before. Rounding error, whatever, it should be 0. I don't know what's going on here. Don't worry about it. And then finally, AC is equal to 2. So we have A is equal to 2 and our C is equal to 2. The end, except for not the end of this video because we've got 20 more minutes still. All right. So we've got A is equal to 2, B is equal to 0, and C is equal to 2, which means that our integral becomes this. We've got the indefinite integral of 2 over, remember the first one was x minus 2, plus it was bx, which is very convenient because we have 0x, which makes that part disappear there. Bx plus c, 2 over x squared minus 4x plus 6, I think. Yep, okay, dx. All right, we're good to go on this one. Sure, you would do a little u substitution on it, like u is equal to x minus 2, du is equal to just dx, so there's nothing to fix on this one. However, notice that this one is no longer in the form of our friend du over u, right? If you were to make the bottom du equal to an x squared minus 4x plus 6, then, whoops, not your du, your u. Then your du would be equal to a 2x minus 4. You're not fixing that. No. However, this is basically the second objective, right? We've got a squared on the bottom. We've got a degree 0 on the top, which means that, hey, this is probably arctangent. And in order to get the arctangent to work, we're going to have to complete the square. So completing the square here just on these variable terms. We have an x squared minus 4x plus a blank, minus the blank plus 6. You take half of the -4, you get -2. You square that, you get 4. We added 4, subtract 4, balance that thing out. We've got x minus 2 quantity squared plus 2. Wow, there's a lot of 2. It's almost as if someone just made up this problem with a whole bunch of 2's in it. I wonder who did that. Anyway, so we've got the definite integral, indefinite integral. What are you talking about? X minus 2 plus 2 over, I'm going to switch the order here, 2 plus x minus 2 squared. My gosh, look at all the 2's. All right, I think we're good to go for the antiderivative now. We already said that this one, we don't have to fix anything with the u substitution, but we still have this 2 out front. So this should be equal to 2 natural log absolute value of x minus 2. Okay, that should be absolute value. Come on. Plus, okay, now on this one, we're going to have to bring out the 2 as well. And then we also have to take into account that a is equal to, well, actually, a squared is equal to 2. So a is equal to the square root of 2. Here, maybe I move this stuff over here. It's crowding up my business. All right, and then my u squared is equal to x minus 2 squared, so u is equal to x minus 2. All right, so then I think we're good to go with the antiderivative, the arctangent part. We have this 2 over our square root of 2. Remember, it's like 1 over a, so we've got 2 over the square root of 2. Just leave it like that, no worries. Arctangent of u over a, x minus 2 over a square root of 2. And after all of that work, do not forget your plus c. So how did you like that? So even though we had this thing here that will not be on the AP exam, I did put together an example for you that used both objectives, partial fraction decomposition, which is what happened right over, well, actually at the very beginning of this, we had to decompose this highly complicated rational function into its partial fractions, right? And then the second one, we had to complete the square right there in order to come up with the arctangent antiderivative. The end.